Good evening, everyone. Thanks for sticking around. My name's Richard. I work at a company called Talko. We have recently released our first application on iOS. Anyone familiar with Talko here? Besides the developers in the back? Anyone else? Great, it's a pretty good showing. And now all of you are going to know about Talko in just a few moments. So Talko, as Peter alluded to, is a new native application sort of trying to rethink how we do conferencing and team communication, really built for mobile, on-the-go teams, distributed teams. Us, ourselves at Talko, are a distributed team in Seattle and San Francisco and here in Boston. And trying to think, how can we make communication for these teams better? Easier to use, better than traditional conferencing systems, better quality audio, integration with other media types, support for both synchronous and asynchronous communication. So, if you can't make a meeting, if you have a developer in Russia or anywhere else that isn't on the same time zone, how can they participate and give feedback and contribute to meetings as well? So that's really what Talko is about. We have a construct that we call a call. It's probably very different than calls that you're familiar with, but it builds upon WebRTC and other technologies that we've built to give a very rich call-like experience. As you can imagine, trying to do all this stuff of bridging, synchronous and asynchronous communication and all this stuff is challenging, and we really wanted to have a lot of time to focus on the user experience and the user model and how things would flow on all that stuff. So, small startup team, we didn't really want to be building a VoIP stack from the ground up, nor did we necessarily have the experience to do so. So, even when we were starting about 2 years ago, WebRTC was a natural choice of, here's a great up-and-coming technology that we could take a bet on that will really help fill a big void in what we were trying to achieve. As Chad alluded to it at the beginning, one of the big drivers for us of choosing WebRTC wasn't about, JavaScript APIs or peer-to-peer connection, but that it's just a best-in-class VoIP engine, and it's free. And startups, we really like the word free. It's open source, which means that we can build it, we can really get into the code, understand what's going on, hopefully help contribute back, and offers all the things that we would want and need in a mobile application. People have spoken about the ICE stack, so I'm not going to go too deep on that right now, but on mobile devices, it's even more important that you have a really good NAT traversal strategy. People are sitting on 4G connections and LTE connections, almost always behind multiple network devices between you and the mobile device. We wanted to have great audio quality, much better than a phone call that you might hear. And we wanted it to be great even on a subpar network connection. And Opus really allows for that with the forward error correction that Chad also discussed. These guys made this part really easy for me. And just provide all these tools to give us a great VoIP stack and let us focus on the portion of it that was unique to our application. So WebRTC is great. WebRTC is awesome. It's been incredible to see how things have evolved over the last 2 years. But there's also been a lot of challenges and learnings, especially building on a mobile device. Before I go into that, I'll give just a very high-level overview of what our architecture looks like. I'm not going to spend too much time discussing our media servers, but in order to support conferencing, we do connect all our clients into a media server. So that is effectively the other peer in our WebRTC, if you think about it in a pure WebRTC way. All clients are always connected to these session servers. That's sort of where your texts and photos and login and registration go through, and those effectively act as the initial rendezvous point. When a client enters a call, we dynamically allocate them to one of our media servers. There are more than two, but for sake of the slide, we'll just pretend that there's two. And so regardless of what session servers you're connected to, everyone in one call, web, Android, iOS, whatever, will all connect into a central media server that's dynamically allocated, and that media server will be responsible for recording all the audio for playback later, providing some rich information to the rest of the application about who's talking, whose mics are open, all sorts of stuff like that. So now we're going to get into the fun stuff. When I think about challenges of building a any mobile application or any real-time application, I really think about breaking them into two groups. So you have network challenges and sort of device-specific challenges. So we're going to go into all of these in a little bit more detail, but on the network side, we're talking about packet loss, jitter, and something more unique to mobile devices is network transition. So people can be walking around, coming and going. You'll pass a Starbucks, you'll connect to their Wi-Fi, you'll drop off onto 4G, you'll walk into your apartment, back onto Wi-Fi. If you're like my boss and you have a very large house, you could bounce between access points. Any of these things could happen. You need to be prepared to deal with that. On the packet loss and jitter front, we'll talk a bit more, but just imagine these are problems for a desktop connected to the internet via hardwire. Just imagine what they're like on your mobile phone walking down Comm Ave or something. On the device side, as amazing as our smartphones are, it's not a desktop PC plugged into the wall. You have real concerns about performance and battery and things like that you need to address. Users will not continue to use your application if you suck their battery dry. Users will not continue to use your application if you run their data allocation from AT&T into the ground. So those are a lot of the places where we've had to invest some extra time while building out our application and working with WebRTC. So the first thing we'll talk a little bit more about is jitter. This is a little graphic that I attempted to put together of what jitter really means to the application. In an ideal world, in voice over IP, you'll get one packet on a regular interval, say 20 milliseconds if you're using Opus, and every 20 milliseconds a new packet will come with 20 milliseconds more data, and everything will be beautiful, and everyone will talk, and the world will be happy. That's not always how it works, especially on mobile. You can get huge bursts. We could go 100 milliseconds and get no data, and then we could be followed by 80 or 100 milliseconds bursted just in one shot. They might all just fly in. There might be some packet loss built in there. So you need to be prepared to handle this. And it's challenging because, how big do you make that buffer to ensure that you don't have any pops or gaps in your audio? If it's too big, the two parties aren't able to communicate anymore because the latency is unmanageable. If it's too small, the quality is going to go down because you're going to have lots of times where you run out of audio to play and you're stuck waiting for more audio to arrive. So this is a huge challenge to deal with. And lucky for us, this is a great part of WebRTC, a module called NetEQ, which has all this incredible logic to sort of measure how your network's performing, adjust a variable buffer of input data, and is even able to sort of accelerate or expand the existing data using fancy math to try to keep the end-to-end latency at a manageable amount for the two endpoints. Fortunately, this is not code you want to write on your own. And lucky for us, we haven't had to. However, being a native application and having this incredible open source code, we are able to sort of get into NetEQ and understand what's going on a little bit, and most importantly for us, gather metrics from it and measure it to understand, what's our end-to-end latency, what's going on, can we maybe explain why a call isn't going well or something like that. So while this isn't a place where we've written a lot of code, it has been great to be able to get into it and really understand it. Packet loss, as we know, it's packet loss, it just doesn't arrive. There's not a whole lot you can do about it, but with Opus FEC, which, as Peter alluded to, was finally implemented this year, makes life a whole lot better. In the past, there's been all these types of algorithms called PLC algorithms, which is packet loss concealment, which basically, once a packet is lost, attempts to use historical data and stuff to take a guess and rebuild what that lost packet might be. With Opus forward error correction, it sort of takes that algorithm to the next level and says every packet will include some amount of information about the packet that came before it. So you can really make a very intelligent reconstruction of the packets that are lost. And in testing that we do, we're able, using the network link conditioner on iOS, which if you're an iOS developer, I highly encourage that you check out, drive the expected packet loss up to 20% and hear almost no pops using FEC. It's really incredible. And the last thing is as I was talking about the network interfaces coming and going, you need to be able to fail over from Wi-Fi to 4G or LTE and give the user some understanding of what's going on if you can't fail over very quickly. So sort of two parts of dealing with this. Number one is ICE, and the ICE connection protocol is your friend. It is constantly gathering candidates for available networks and sort of assists in the swap over from one network to another because, basically when your Wi-Fi network goes away, it'll start saying, hey, there's no Wi-Fi candidates anymore. Here's some 4G and LTE candidates that you might prefer and try to connect to. And so that's one part of it. The other part is, this is when we start talking about integrating with the native APIs on a device to enhance the experience. On iOS, there's an API called Reachability. There's similar things on Android where it can actually tell you, you're connected to a Wi-Fi network right now. You're connected to 4G, LTE, whatever. And you can use that as extra data both to expose to the user what's going on and potentially feed input into the WebRTC stack about, hey, there's been a hard failure here. Don't bother trying anymore. Favor this other network instead. As I'll talk to a little bit more, I'll just get to in a second. So moving on to device-side challenges. The biggest thing is battery. At the end of the day, we're talking about your application can't run if the device dies. So you need to try your best to consume as little battery as possible and keep your users happy. They're on Facebook, they're emailing, Instagramming, whatever. You don't want to take a 20-minute call and run the battery to zero. So this was a place where we ran into some challenges with WebRTC at first. We saw what we considered a not acceptable amount of battery consumption over test calls that we were running. And then one of the first things we found is that by default, for this failover I was just alluding to, that WebRTC effectively is keeping both radios on your mobile device awake at all times. The WWAN, which is 4G LTE radio, as well as your Wi-Fi radio. These devices would prefer to only keep one of these radios up at any given time and just run all communication over that. The downside of that is that your failover, should you lose Wi-Fi and move to 4G or LTE, will be slower if you're not gathering on both. But the battery loss we found or the battery gain if you stopped listening on both simultaneously was tremendous. We're talking about like 50%. So if a call was consuming 20% of your battery over 20 minutes before, now we're talking about 10%. It's a really noticeable benefit. And if you think about, and we decided, for this trade-off that our users would most benefit from the battery win and give up some time on failover. Now that's a choice you have to make on your own. But fortunately, now in WebRTC, there's actually, if you're a native developer, this is C++ code, there's an interface called set network ignore list where you can pass in, ignore the WWAN interface or ignore the Wi-Fi interface. And so if you hook into your reachability or whatever API your phone provides and then funnel that into WebRTC, you can effectively do this and disable whichever one of the radios aren't currently in use. So that's great. The other thing is CPU. CPU obviously has ties to battery, but mobile devices will also limit the amount of CPU or the amount of time you can actually get to run on a core as an application. On a desktop, if I say, I need a real-time thread so I can wake up every 20 milliseconds and run my capture and render, you get your real-time thread, it calls back, all is well in the world. You request a real-time thread on iOS, the highest priority you're going to get is 47. To put that in comparison, the thread that updates the UI would run at a priority somewhere in the 90s. So this is nowhere near real time. It's not reliable, and what that means to the end user is that there'll be pops and gaps, because rather than waking up and capturing 20 milliseconds of audio every 20 milliseconds, there might be 30 milliseconds between sleeps, or 40 or 60 or 80. So that's not good. So what we found was that we could move a lot of that processing off of the custom WebRTC threads and onto an iOS audio thread, which is provided to you. This is part of the audio unit or audio graph APIs, and this is basically where the system calls you back and says, I've captured new data from the microphone, or I need more data to play out. And so what we did is we moved a majority of the capture and render work onto that thread. What that means is that now we have the real-time priority thread that we need to run a truly performant system. It also reduces the number of overall threads in the system, which for mobile is great. The one warning I'll say here is that we had to do a lot of work to remove excess locking and logging and things like that, because you have a very limited amount of time on this thread, or you'll get cut off. If you're getting called back every 20 milliseconds, that means you have at most 20 milliseconds to do all your work, including sending data over the network, things like that. The last bit about things to think about when building a mobile application specific for media is that you want to integrate into as many native APIs as possible. Give the user that rich native experience that you can have when you're building for a specific platform. This starts with requesting permissions. Chad showed on the web, you get a banner, accept or reject permissions. You have to do the same thing on native devices, but it's up to you to decide how to do this, when to present these dialogues and things like that. We have found that it's very important that you ask for permissions only when you need them, and attempt to give a very clear explanation, or let the UI give a clear explanation of why you need them. So the users have a sense of trust that, oh, I'm about to grant you access to my microphone, but we'll only use it when you push the button, not, on in your pocket recording everything. So I'd say be very careful about when you ask for permissions, but at the same time, be sure that you get, it's important that you do it at the right time, or the user might say no. If you don't get the microphone, there's no point in any of this threading or locking work or any of this other stuff that we've discussed. The next part is integrating into the core audio stack, letting a user connect to Bluetooth so they can use it in their car when they're driving around. Being sure that you handle interruptions. With a device like my iPhone, it can only play out audio from one primary application at a time. So if a phone call comes in, you get cut off. If the user flips to Spotify and hits play, you might get cut off. And when they come back, you want to properly recover, ease back in, make sure they understand what happened, and things like that. And the last bit, which I mentioned, was integrating into reachability. So with that, I hope I left some time for questions. That's all I have. Yeah, in the front.
How careful do you need to be about Apple's App Store permission thing with these APIs, looking into microphone apps and things like that?
So Apple actually provides and documents these APIs for requesting microphone permissions and things like that.
Time with permissions, time with high priority thread.
So they give guidance on this high priority thread, and they say, you better not run over time or you're going to get cut off. And then they have a list of things that you shouldn't be doing. Things that are costly, like logging and locking and sending things over the network. But none of these things are strictly prohibited. So it's totally up to you. But you just need to remember that you're running under a very tight amount of time. So if you take 25 milliseconds to execute, they're just going to skip the next time they call you back, and you won't get called back for another 35 milliseconds. So it's really important that you keep under that time. But what you do in that time is up to you.
One last question.
Yeah.
You showed the first picture. Was the media server, are they co-located for the same session, or you spreading across different media servers for all the calls in the session?
So all the users in a single call who are communicating are on a single media server. But if they all exit and come back, they might get routed to a different one the next time. We are deploying into the cloud. We're constantly deploying new servers and new code multiple times a week. So by the time you come back, there could very well be a new server.
So within a session, you'll be in a single media server?
Yes.
Is the Ethernet designed by the Talko part of the WebRTC?
What was that?
Is the EQNet or NetEQ? It's part of WebRTC?
It's part of WebRTC, yeah. It's a part of WebRTC that we've spent a lot of time sort of understanding deeper and trying to find some bugs and sending those back to Google. But that's something that runs in your web browser or in any other WebRTC stack you're using. That's a core part of Google.
As you mentioned, you will use the local buffer. You try to use the local buffer, the client buffer, to monitor and mirror it based on that information.
Yeah.
To try to get to extend the network service. So I'm curious, how possible a local client buffer size would be helpful for you to measure the network, like do the congestion control?
Sure. So we try to keep, ideally, we'd see buffer sizes of, we're talking about 200 milliseconds or less. Users can sometimes tolerate about up to half a second. Anything over that, you start to get to the point of something that is a conversation that's really hard to have, like you're talking to like the far side of the world on an old phone, or like talking to Mars or to space. Sometimes we see the latency spike up to close to 1 second, but what the module will do then is it'll accelerate remaining audio and try to get you back down to a happy level.
But the congestion level is totally decided by all the components through the whole network. The congestion will be the key reason to cause that.
Absolutely, yeah. I mean, especially with the cloud, there can be congestion at many points, but NetEQ is focused on especially dealing with the jitter of stuff coming into the client and ensuring that you can get a smooth stream of audio out to the earpiece or the speaker or whatever. It's not, whatever congestion happens above it is done and passed by the time it lands at the client, and its real goal is to give a smooth experience at the end.
Okay. So the second question I want to ask about how the current the Talko architecture, communication architecture will get used to the WebRTC 1.1, because as you mentioned, current design is based on the P2P connection, right? However, in the next 1.1, they don't have P connection anymore.
Sure. So since we have our own fork of Google, we can of the Google WebRTC that we've built into our native stack, we can choose to update when we're ready to. But at the end, even though the peer connection API isn't there, it's still going to be a connection from one endpoint to the other, and it's going to be based on a lot of the same principles. The API might change, but we're still talking about as Peter was alluding to, ICE and RTP and DTLS, and a lot of that isn't going to change.
Okay. Yeah. Thank you.
You can do one more question if there's another one.
And there's not.
No. All right. Thank you. That
Anyone?
was great.